This is my talk. It's the title is a joke because life's a joke right now. Black holes and revelations, musings on the hopes and expectations for gravitational waves and how they were met and what's still to come, which is a mouthful, all for fun. So, let's get into it. I'm Dr. Brynley Pearlstone. Famously, I'm a triple threat. I've got a PhD in astrophysics from the University of Glasgow. I'm an independent science communicator, and now I'm the host of Psycherius podcast, which is, as you can see, the podcast that highlights LGBT people in STEM and gets to know the queer side of science. I've been doing that now for a little bit over a year, and I'm very glad to have an online form of science communication during the end of the world, which is great. So I just want to unpack what's going to be in this talk before we begin. There's going to be a couple of minutes of primers. So what is gravity and how does it work? You know equations that will all be hand wavy, don't worry, not a test. There'll be a primer on compact objects. What do we mean by compact? What do we mean by object? And what do we mean by compact object? A little bit of gravitational wave history, starting with theorization through till today-ish. We'll talk a bit about LIGO, the first detections that what we learned, binary black hole and binary neutron star systems in particular, where the field is today, and what we expect to come in the future. So lots of ground to cover, and let's dive right in. So in the beginning of everything, there wasn't much at all. In fact, there was nothing. And then something happened that we call the Big Bang. And in that moment, all of space and all of time sort of just popped into being. No one really understands it. And if they do, take that with a pinch of salt, because no one should understand it. You can get back to something like 10 to the minus 32 seconds after the Big Bang, which is pretty much instant, but not exactly what happened or before the Big Bang. So always pinch of salt if you hear about at the Big Bang or before the Big Bang. In that moment, all of space and all of time was created. And in this sense, space is just sort of a metric. You can think of it as a grid. And with space and time, we also get gravity. Now, Einstein was very clever. He kind of formulated our modern understanding of gravity. He was clever. He also married his cousin. Probably not a good role model. Oh, my wraparound text is not wrapped around. That's really annoying. Okay, I'm gonna have to. So he formulated the general theory of relativity, published it in 1915. And that just says that heavy objects will bend and curve space and time, as you can see in this GIF. GR isn't really a law, it's a set of equations that describe a system. And as with any set of equations, you can have one or many solutions. Gravity is one such solution, about a well things can fall into, but there are a bunch of others. I've got a favorite. I think a lot of astrophysicists have a favorite space-time. But one of these such valid solutions is what's called a plane wave. Plane wave is a common solution to a whole bunch of equations because we know how sines and cosines work, and so we try and jam it into anywhere it might fit. That plane wave solution describes what we call gravitational waves. In this sort of analogy, we can think of space-time as heat, where gravity is a well that things can fall into, and gravitational waves are ripples, like you can see in the GIF on the left-hand side. Now, that's a reasonable analogy. It's not exactly perfect for one thing, but we're doing hand wavy, and I don't have 20 hours to teach you, and I wouldn't want to. The thing to remember with this is that space-time is very stiff as a material. So in order to get anything to move, to wibble or to wobble or to deform, you need to pump a lot of energy into it, whether that's of mass in the form of energy in the form of mass, or in the form of acceleration. You just need to really throw it at the wall and hope that it sticks to space and time. Some things like gravitational waves, because that is, after all, what the talk is about. Gravitational waves travel at the speed of light, at least in theory they do, because that's the speed of the metric of the universe. They can come in two polarization components. Now we think of polarization as sort of the orientation of the wave. In gravitational wave, there's a plus component, which is perpendicularly sort of up and along. There's also a cross component, which is at 45 degrees to that. and they are the two components that gravitational waves can polarize. You can see in the GIF on the left-hand side, a plus polarized gravitational wave as it goes through a tube. And you can see that in form of stretches and squeezes. Because that's what gravitational waves do. They have the effect of stretching space-time in one direction. As it stretches out, squeezes in another direction. So you can be short and fatter as one gravitational wave passes you, and the next instant you can be tall and thinner. But as I say, space-time is very stiff, and gravitational waves tend to have to travel a very, very long way. So the effect of gravitational waves that we will ever encounter is remarkably tiny, absolutely minuscule. And we get into the numbers on that a little bit later on when we talk about some real-world examples. So let's fast forward a few billion years from the Big Bang. And stars are formed, and then they are subsequently burned out, and we're left with the sort of cores of stars once they're burned, neutron stars and black holes. And these are incredibly dense objects. And we call these compact objects because not only are they dense and heavy, they're also very, very small. And these compact objects are exactly the kind of storm in a bottle that we need to generate really, 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 really freaking loud, violent events. And these are the kind of events that can pump enough energy right into the universe to give us a gravitational wave. So, moving on. So among these neutron stars. And neutron stars are weird. They're absolutely bizarre. They were first theorized and discovered between 1955 and 1970. Big shout to my girl, Jocelyn Bell Burnell, for the discovery. The whole story there, don't get me started, I will chew your ear off. What a neutron star really is, you take a star, right, and you kill it, so it's burned through all its energy. And the heat from the core that is no longer there. And so all the mass of the star is no longer being held up by the pressure generated by the heat burning in the center, and it all falls in itself and squeezes it in so hard, it sort of starts to overcome the Pauli exclusion principle, which is some quantum physics thing about two particles not being in the same state. As such, all the matter can get squeezed into the most dense form that it can be. And so you're left with all neutrons, pretty much, which are one of the fundamental particles inside of an atom, a ball of neutrons with as much mass as our sun, but that fit into a space about the size of Greater Glasgow. So incredibly dense, incredible cosmic power, and itty-bitty little living space. They're made entirely of neutrons. The crust of a neutron star, and that's the bit that is on the outside, crust, they tend to crystallize into sort of clumps of iron atoms, IRONFE, because that's the most stable atomic nucleus. And in the inside of the neutron star, it stays as sort of nuclear matter, but nuclear matter is weird and we don't really understand it all. And so we think it's a superfluid, which is a weird thing where if you were to start a wave in a bucket of superfluid, the wave would last longer than the length of the lifetime of the universe. Superfluids be crazy. Because of this, we don't really understand neutron stars. There's this concept in physics of the equation of state, which is a set of equations which describes how matter behaves. Now, we don't have a good constraint on the equation of state for the neutron star. So there's still this big mystery to us. And that's one thing that we can sort of glean with gravitational waves, hopefully. But that's weird. They've got crazy, and I mean crazy strong magnetic fields. When we have solar winds that interact with Earth's magnetic field, we get the aurora borealis and the aurora australis, the northern and southern lights. In the GIF that you see on the left, it depicts a neutron star rotating, and those two beams that are beaming out of it are the intense northern and southern lights at its magnetic poles generated by its huge magnetic field. Absolutely insane. They spin. Stars tend to rotate. Our sun rotates something like once every, I wouldn't say 11 years, but don't count me on that. And once a star like that collapses, all that angular momentum has to be preserved, and now it's so much smaller that they spin a handful of times a second. They can be in isolation, like the one in the GIF on the left, or they can be in a binary system. And that just means when you've got two stars together and one sort of blows up, it still orbits each other. When that happens, it can accrete matter, and that means it sort of sucks matter off of the sun and it falls into the neutron star. And just like with a hoop and a stick, when you're hitting the hoop, it speeds up the neutron star. And that's how you can get neutron stars that spin up to faster and faster and faster frequencies. And so you can sort of tell the age of a neutron star based on its spin frequency. They're actually relatively common. There's somewhere between 1 million and 100 million neutron stars in our galaxy alone. That doesn't sound like a lot, but it is, given the age of the universe, how long it takes stars to die. At least that's a number we theorize. And so we, I think that's taken from population studies of the local universe and then extrapolating. Another primer for you, black when something gets so dense that it falls in itself a bit like a neutron star does, it can become a neutron star. If it's any more dense than that, then what happens is the structure of matter cannot contain the mass that it's got, and it keeps falling in and in on itself, and you get this singularity in space and time, and that's what's called a black hole. It really does stretch some of the laws of physics. If you were to approach a black hole, if you were to look into the future, instead of seeing a timeline, you would see a progression of space that leads you towards the center of the black hole. It sort of twists space and time together. I don't really understand what that means, but it means that there's no way out. In fact, the gravity around a black hole is so strong that it bends light. And so you get this lensing effect. So on this GIF on the left, we've got two black holes orbiting each other. There's a smaller one and a larger one. And you can see that they're bending light between them. So when the smaller one is in front, you can actually see the outline of it, even though it's black on black, because the background is being bent around each other so much. But they're real weird as well. So compact objects can form compact binaries. And that's a system of two compact objects orbiting each other. And that can come in three flavors, whether it's a binary black hole, which is two black holes, two neutron stars, which is binary neutron star, or a neutron star black hole binary. Over billions of years, as they orbit around each other, they radiate away energy and they draw closer and closer together, and they spin faster and faster and faster. As they do, they fall in closer and closer and they radiate away more energy. And in doing so, they produce some of the loudest and most violent events in the known universe. So they're kind of cool in that way. It does take billions of years from being a relatively stable, slow state to being in the final state. But in the final hours, it gets really quite violent. And in the first observation of a black hole merger, in the last 0.2 seconds of its merger, it radiated away more power than all of the stars in the known universe radiated in light. So they are really, really powerful. Neutron stars, because they are matter, black holes not really matter, just sort of a weird anomaly. Neutron stars are matter, and so they can get ripped apart. So if you've got two neutron stars very, very close to each other as they're orbiting around, the tidal forces, sort of that pull on one side stronger than the other, can start to pull apart the neutron star and start to spill its guts all over space. And that's really interesting in terms of looking inside of a neutron star, because then you get a window into what is happening on the inside. And you can, in fact, compute the orbital paths of compact binaries using general relativity and an approximation called numerical relativity. However, it's very expensive to do so. Every pair of objects and every different alignment is going to look a bit different. Neutron stars and black holes both have an intrinsic spin to themselves, like a top, and that changes how things evolve. And so there's something like 16 parameters that go into these computations. So it's very expensive to do. So what we tend to do is compute a handful and sort of interpolate between them, but even that's really tricky work. So, bringing all this together into questions that we have that we think gravitational waves might be able to answer. Are gravitational waves real or just a nice theory? Does our theory of gravity hold in the most extreme cases? Are black holes real? Neutron stars, what the fuck are you going on about? Can we measure the expansion rate of the universe? Individual asymmetric neutron stars produce gravitational waves. Can we estimate the black hole neutron star population? There's a whole bunch of questions, really big questions about the universe that we can answer just about these two kinds of objects. We'll come back around to this slide later on. Gravitational wave experiments, as told by clip art and some GIFs I found online. So first of all, we've got Einstein. In 1915, he theorized general relativity, came up with a set of equations. He said, gravitational waves are going to be so tiny, I very much doubt they will ever be detected. Or something like that in German. I don't speak any German. Next, in the empty gap, there should have been a cylinder, a shiny silver cylinder, to represent resonant bar detectors. In the 50s, 60s, and early 70s, there was an effort by physicists to get gravitational waves detected using bar detectors. Essentially, a cylinder of crystalline metal, often titanium or tungsten, which is specifically designed to resonate at frequencies that we expect gravitational waves to sweep through. Then, if a gravitational wave were to pass through it, it would resonate and ping, and someone would say something. And in fact, in 1969, Joseph Weber, who was a physicist working on this kind of detector, and his Weber bar, published a result that said that there was an event that was caught by his Weber bar. It was not verified, and so it's not being classed as a detection, because one observation does not make a case. Then in the 80s, a bunch of people led by Rainer Weiss and Kip Thorne and Drever came up with LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory. And they pitched it to a whole bunch of funders, and by 1990, construction was beginning. So then on the bottom right, we've got the initial runs of LIGO, which span, I think, from 2001 to 2010, 9 years of operation during the initial LIGO phase, through which nothing was found, but a whole bunch was learned, which is really critical for the next phase, because in advanced LIGO, center middle, we got some real detections, which is fantastic for a bunch of people's careers and livelihoods and science enthusiasts. And then finally, in the bottom left, there's going to be something in the future. Hopefully not badly animated sharks, but we'll see. So, enter LIGO stage left. It's the Laser Interferometer Gravitational Wave Observatory. And it was a really massive undertaking. They started constructing it in 1990, didn't start observing till, I think, 2001. So it was 11 years just to construct it. 4 kilometers of vacuum tubes carrying high power laser beams up and down. And these lasers were to bounce off mirrors made of fused silica, which were suspended on piano wire pendulums for the initial LIGO. And had roughly a $1 billion project plan and a 30-year plan. Also, they made 2 of them. One detector is not enough. Like I said, one observation does not a good case make. So by making 2 detectors that are separated by a few thousand miles, one in the northwest of America and one in the southeast of America, you can get truly independent readings from very, very similar devices. How does it work? So it's an interferometer, which measures interference, interferometer. So a beam splitter splits a laser beam, which then travels down 2 perpendicular arms, bounces off mirrors at the end, back, and the 2 paths will interfere with each other. Now, if you're watching the GIF on the left-hand side, it's a pretty good description of what's going on, much easier to understand than I think hearing it words alone. When the lasers do recombine, if there's been no gravitational wave, then they will interfere destructively and get no laser output. But a gravitational wave effectively the length of the arms of the interferometer, so stretching in one direction while squeezing the other one. And so you get a different time of flight down each arm. So when the laser beam returns, the two will be out of phase and you get some interference. And that way you can measure gravitational waves, at least so the theory goes. They switched it on, and within a few days of switching it on, there was a ping. They were in what's called an engineering run, where everything's good, everything's locked in place, but they're not releasing it as official data yet. And they got a big ping. So everyone was a bit confused, and everyone was dashing about, and no one could really quite believe it, because who'd have thought that you'd spend 25 years making this machine? The first run would last 11 years. You wouldn't find anything. You spend 5 years doing upgrades, making a higher power laser, 4-stage mirror suspensions, with few silica fibers to hang the mirrors off, and suddenly there's a massive gravitational wave at your doorstep. There was so much effort gone into verifying it and writing the paper. Spent 5 months just writing the paper to get it just right. Everyone knew this was going to be a big deal. And what we saw is GW150914. That stands for gravitational wave that was seen in the year 2015 on the September 14th. And what we saw was a binary black hole merger. So two black holes, one about 30 solar masses, and one about 35 solar masses, orbiting around each other, 1.4 billion light years away, and falling into each other. We detected a signal that lasted about 0.2 seconds, and we detected the gravitational waves from it as a pattern in this interference. There's a whole bunch of pipelines and code and statistics that went into determining that it was a gravitational wave, how it was a gravitational wave, and parameter estimation for the components of it, which I'm not going to go into here. That's not really what this talk is about. And because it was black holes, there was no light produced. Black holes don't radiate light, that's why they're black. But through the collision, 3 times the mass of the sun was lost in energy. E equals mc squared. That m there is 3 times the mass of our sun. And we think that was all radiated away in gravitational waves. I told you space-time was stiff, and you need to just throw energy at it. So the resulting black hole was 62 times the mass of our sun. And for those 3 solar masses, LIGO was able to measure a displacement in its mirrors of 1/10,000th width. Is 0.0 with 19 zeros, 1 meters. And they can do all this with super clever trickery that I can get into a bit later on, but I don't want to get into now because it's really hard to structure, if anything else. But everything about this was absolutely unprecedented and absolutely stunning. Nobody expected it quite so soon. No one expected it to be quite so clear. What we can see on the left-hand side, the top panel shows the data that we received during this event. The second panel shows what the theory predicts for an event like this. The third panel shows you one minus the other. And the fourth shows you time on the x-axis, frequency on the y-axis, and a heat map showing blue where there's not much signal, yellows where there's more, and red when there's a lot. Not a lot of red there. It wasn't entirely that loud. But what you can see is that the theory matches up really well to the observation, so that the residue, this third panel, doesn't really look that different with or without the gravitational wave, which is sort of exactly what you want to see if you're looking for a detection. And it was, of course, detected in 2 detectors, because one don't mean nothing. And it was detected with really high significance, which was great. It was the first direct observation of gravitational waves. There have been prior indirect observations, but this was the first direct observation. It answers the question about general relativity standing up in the strong field, i.e. black holes banging together. And it definitively shows that LIGO can work. It was 25 years getting there, and $1 billion project. It was really nice to get that sort of validation for the project. Not only that, there's also the very first direct observation of black holes. There's been indirect observation of black holes before, but never a direct observation. And that's because they don't emit any light. So you can't see them with a regular telescope unless you use one the size of the Earth. We're also able to measure the distance, the inclination angle of the binary black hole, the individual spins of the black hole, the energy lost. There's a whole bunch you can measure just from this waveform. It's probably a bit of just wait. So after the first observation run, we get Virgo join. Virgo is the European equivalent to Advanced LIGO. It is just outside of Pisa in Italy, and has some slight differences to LIGO. They use slightly different mechanics to suspend the mirrors. They use different power. The arms are a different length, I think. But it's vitally important to have a third detector, because a third detector allows for much, much better localization of the source in the sky. A gravitational wave detector isn't like a telescope. You don't point it somewhere and see something. With a gravitational wave detector, it's more like an ear. You need two of them and a complex arrangement to sort of get any idea where something's coming from. So you, with one detector, you sort of know it's somewhere around you. With two, you can measure the time of flight of the gravitational wave from one to the other. And you can constrain the location of the source to a ring on the sky. With three, you get 3 rings on the sky, and they only intersect at a certain point. And so you know, to a pretty good degree, where that is. So Virgo is this European detector, and it came online in 2017 in the Advanced LIGO's second observing run, which we will get to, I think, just now. So when we switched it back on in November 2016, there was a slight sensitivity increase in LIGO. Virgo was online now, but it was not very sensitive in comparison with LIGO. So where LIGO could see a certain type of event out to maybe 80 megaparsecs, Virgo could only see that kind of event out to 20 megaparsecs. You don't need to know what a megaparsec is here. That it sees a quarter of this distance is what's really important. A quarter of the distance doesn't mean a quarter of the number of events either, because the number of events scales with the cube of the distance, because we're looking at a sphere in the sky as opposed to just a one-dimensional track. So 4 times more sensitivity distance means 64 times as many. 64 times as many. Is that right? No, 48. 48 times as many events that you can capture. And true enough, in O2, we did capture a whole bunch more events. We observed 5 more binary black hole events, of which I think 3 were observed with 3 detectors, and we were able to constrain them on the sky. The picture on the left shows you the difference between a 2-detector observation, which is this banana shape in blue in the middle, and a 3-detector observation, which is this yellow splodge in the middle of the banana. So really, having 3 detectors online, even if one isn't anywhere near as sensitive, is really a boon for the science that we can do with this. And that came in handy for GW 1708-17, Gravitational Wave on the 17th of August, 2017. It was the direct observation of neutron stars merging together. Because of the 3-detector configuration, we were actually able to pinpoint it to really, really, really narrow spots in the sky. So much so that astronomers who were given a very, very quick alert sent out after the trigger at LIGO was set off, astronomers were able to find the host galaxy and start observing there and have a look for light components that followed this explosion. Because these aren't black holes, we do expect that they'll give off light. In fact, the GIF on the left-hand side shows you a process called a kilonova, which is what happens when two neutron stars merge. They merge together, and as they get close, they rip each other apart with tidal forces, spewing nuclear matter into the space around them. And then they shine bright for a few days. And that means we can do a whole bunch of science with it. So what are we looking for here? So I said nuclear matter thrown around. That nuclear matter then decays, and that means that it puts off radioactivity. It emits all kinds of gamma rays and alpha and beta particles, which you can pick up with optical telescopes. And in doing so, it decays to precious metals. So I think 1 Earth mass of gold was created in 1 instant alone, as well as a butt ton, that's a technical term, a butt ton of platinum and silver and all these heavy metals that don't really get made in normal stars burning up. This is where they come from. At the moment of merger, there's a massive release of X-rays as well. You get particle beams off of the top and bottom of the merger, which are, I think, gamma rays. The result is hot, and you end up with hot dust around the merger. And that can be picked up on infrared and radio. Basically, it's just a feast with telescopes all over the place. And the result, we think, is a quasi-stable neutron star that is too big to really remain as a neutron star, so it very quickly decays into a black hole. So all of that is a feast for science. In the GIF on the left-hand side, you can actually see the host galaxy and the kilonova spot brightening up and dimming again. So not only were we able to see it gravitationally, but really we were able to see it very clearly optically. And that provided a whole bunch of science. There was an independent measure of the Hubble constant, which was super important because the Hubble constant measures the growth rate of the universe. There are currently 2 optical measurement techniques, and they do not agree with each other. So a third independent measurement is really key. It verified that kilonovae, that explosion that you saw on the previous slide, are caused by binary neutron star in spirals. Verification that heavy metals are created by this kind of explosion. Because you had an optical counterpart and you had a gravitational wave counterpart, you can measure the speed of gravitational waves relative to the speed of light and constrain that they do travel just about the same speed. With it, you're able to estimate the small population of neutron stars, because suddenly you've seen 2, you know there's more out there. And clear evidence that a 3 detector network is invaluable. If you're going to have gravitational wave detectors, you need 3. So after that, not shortly after that, a couple of years after that, April 1st, 2019, LIGO begins its 3rd observation run, which we call O3. That observation run ended, I think, March 23rd. Thank you, COVID-19. Closed down for health reasons. The majority of the run was a 3 detector configuration with LIGO, LIGO, and Virgo. Virgo dropped in and out for upgrades now and again. I think there was a month break in October where there were upgrades at LIGO as well. And in February of this year, Kagra, which is a Japanese experiment, which is inside of a mountain, really fascinatingly, joined to make it, very briefly, a 4 detector configuration. So throughout this roughly 1 year span, there were about 1 detection every week. And that's whether it's a neutron star binary, black hole binary, neutron star, black holes, 1 neutron star, 1 black hole. Obviously, 1 a week is far too much to keep up with, given that the first one took 5 months to write a paper and do the analysis for. So nowadays, almost all of the analysis and paper writing and distributing of data is automated, which takes a whole load off for the scientists who are doing that work. So now we really do enter the house of abundance, which is the GIF on the left-hand side from FX's pose, because abundance and yeah. So let's bring it all back together. Are gravitational waves real, or is this a nice theory? Yes, they're real. Does our theory of gravity hold in the most extreme cases? Yes, it does, and really well. Are black holes real, or just a nice theory? We think they're real. At least the model that we have fits with the observations of them. And now we've got an optical observation of them as well. Neutron stars, what's going on? Still a lot of unanswered questions there, but we've got a whole bunch answered. We know that kilonovae are a result of merging neutron stars. We know that heavy metals are a result of neutron stars merging. We still don't know an awful lot about the equation of state, but we've managed to constrain it a little bit. Can we measure the expansion rate of the universe with gravitational waves? Yes, but at the moment, we haven't constrained it very well to be very much help at all. But we can get there eventually. Can individual asymmetric neutron stars produce gravitational waves? Don't know yet. That was my thesis, so I can talk your ear off on that as well. I didn't really touch on it in this presentation because it's not the highfalutin fancy bit that everyone loves. Can we estimate black hole neutron star population with gravitational waves? Yes, and we did. I don't have the numbers to hand, but I can come up with something. So for gravitational waves, 04 is due to start at some time. I don't know when. I'm not in the collaboration anymore. I can't sit with them. And that will likely be a 4-detector era. Whether that's 2 LIGOs, Virgo and Kagra, or the LIGO India detector that will come online. We look forward to having cryogenic detectors. Kagra in Japan is going to be a cryogenic detector if it isn't already. There are plans for a 3rd generation of gravitational wave detectors, including ET, which is the Einstein telescope proposed 3-prong detector based somewhere in Europe. LIGO Voyager, which is to be an expansion to LIGO. And that will be big, probably cryogenic and perhaps longer baselines. So rather than 4-kilometer arms, perhaps even longer. On top of that, there are a whole bunch of really exciting space-based missions, including ELISA, which is a constellation of 3 satellites, which will orbit the sun behind the Earth, tumbling as they orbit. And these 3 make up a triangle, which is essentially 3 interferometers. Their distance is something like 5 times 10 to the 5 kilometers, something like that. It's crazy big. And DESIGO, which I don't know much about, but it's supposed to be a decihertz interferometer. Other sources are going to be hopeful in these next few years as the detectors get more and more sensitive. Whether they're isolated rotating neutron stars or the background of unresolvable binaries that merge together far from the universe that create sort of this background murmur noise. And so many more multi-messenger observations as neutrino technology comes along and optical technology catches up with the state of the art for gravitational waves. There's so much here to explore, and I can't wait for it all to unfold. So just to close off, I want to say thank you to LIGO for the images, for the science, for overall positive years, to Giphy and Google and all the myriad references for the GIF that I've used, for Christopher Berry for the optical schematic that I used a while back, and thanks, I think most of all, to Matthew for turning around the Stone Village Symposium so quickly and putting this platform for all of us to give a talk. Thank you. So if anybody's got any questions, I am here for them.